see a few more people coming, and okay, so now let's start with the next talk, which is by Sandra. Unfortunately, she's one more victim of the air travels because her flight also got canceled, but luckily she agreed to give a talk remotely. So thank you very much for joining us remotely, and please let's continue with your talk. I will also monitor if anyone is on Zoom. I will monitor questions, but otherwise, we'll just proceed, raise hand, and wait until I give you microphone to ask questions. Okay? Thank you. Please, Sandra,
Thank you very much. Thank you, first of all, for the invitation. I'm sorry that I couldn't make it. I'm really disappointed because I was very much looking forward to being there and connecting more to the formal methods community. I'm more from the machine learning side of things. And my daughter was particularly disappointed because she wanted to go shopping in California. But anyway, here we are. I'm very sorry. And I hope that we can make the best out of this. And I hope to have another chance to come out and meet some of you. My talk is about formal models and methods of active learning from contrastive examples. And the reason I think it might interest some of you is because I believe it has some connections to Oracle-guided synthesis. This is ongoing work. We just have our first paper under review right now. My PhD student Farnam is working with me on this, and my colleagues Hans, Adish, and Ushin. And yeah, I'm really glad to have the opportunity to present this work to you here. So I just want to give you a motivating little intuitive example at first. We want to learn with a machine learning method, a classifier that looks at a picture and says, does it show a bass guitar or not? And you can imagine you're feeding this the learning algorithm with labeled examples. So you have a few here that are not bass guitars, clearly not bass guitars. And this one you say is a bass guitar. And the classifier, there's a classifier trained on these examples. Now you can imagine that this classifier will be much more accurate and learn maybe the concept bass guitar a little bit faster if you also presented with this example in addition, right? Because this, compared to the other negative examples, this acoustic guitar looks much closer to the bass guitar than the others. It's much more similar, but yet it's not a bass guitar. So this is what I would intuitively call a contrastive example to that photo on the left of the bass guitar that maybe helps draw the decision boundary much more accurately than the other examples. So in this talk, I will introduce a formal method of what it might mean to learn from contrastive examples, and I show you some of our first results on this model. So intuitively, we would think that if our training data points contain a contrastive example, or a pair of contrastive example, like these two guitars, then learning an accurate classifier can happen more quickly, meaning from fewer training data points. And the number of training data points is often a big issue, especially in training neural networks. It can be really a bottleneck. In our work, we're taking this idea one step further. So we're cranking it up a notch. We're saying we can learn highly accurate classifiers yet even faster, meaning from even fewer training data points, if the learner, in addition, knows that this is a contrastive example. Not just, here's another example, but being told this example is contrastive to the other one you've seen. So if we tell these two instruments here in the top, in the bottom right corner, those are contrastive examples. The learner can extract something in addition from that knowledge. How do we do that? To explain the formal model, I first have to introduce just a little bit of basic concepts and notations behind that. And we will study everything in the model of concept classes. What's a concept class? Okay, concept class is just a set of subsets of a domain. So we have a domain X. X could be the RM. It could be an m-dimensional, like a box bounded in the RM. of the unit interval, or we could have the Boolean domain over m Boolean variables. A concept is just a subset of that domain. So a concept we usually denote by C. C is a subset of X, but we also use C as a function. So C of X is labeled 1 if X belongs to C. So the indicator function, 0 otherwise. We use those notations interchangeably. For example, C could be a threshold function over the unit interval, or C could be the set of all truth assignments to a Boolean formula. And a concept class is then just a set of concepts. For example, the set of all threshold functions over the unit interval, or the set of all monomials and m variables, anything like that. In our learning models that we look at, I try to sort of schematically break down here a whole bunch of learning models that we consider in computational learning theory. Here, I assume that the learning algorithm knows the concept class C, so it knows I'm supposed to learn a threshold function or something like that. And there are two parties involved, the learner on the one side, but on the other side, the oracle. And I assume the oracle now selects from that concept class a target concept C star. So that's the unknown concept for the learner. Learner has to identify the C star. What does the learner do? The learner will first, in step 1, initialize its version space. What's the version space? That is simply the set of candidates for the target concept C star. So anything in that version space is what the learner is still considering as the possible target. Then the learning algorithm will somehow miraculously receive a labeled example. That is a pair where X is an element of the domain and C star of X is the true label of the target concept under that, example X, right? And then the learner will update the version space based on the example it has seen. What does that mean? Well, it will keep in the version space all of the concepts from before for which the label for X is the same as that label C star of X which it has seen. So the ones that are consistent with the information with those labeled examples that it has seen. If that version space now happens to have cardinality 1, that means there's only one concept left as a candidate, then I'm done with learning. That has to be the true target. And then I stop, else I repeat. I will request another labeled example and so on. Now, what happens in the contrastive setting that we want to look at? We now assume that the oracle presents, after that example for X has been received, the oracle presents a contrastive example for X to the learner. That's an example X prime with its correct label, where X prime has to be selected from some set CS that depends on the target and on the example X that was just chosen, this example here. So what do we mean by that? That set CS is intuitively the set of permissible contrastive examples for X. How this is exactly defined, we will get into that later. For now, you just have to know there's a set of allowable contrastive examples depending on X, and the oracle picks one of them. Now, what happens in the version space update? Remember that in the traditional version space update, we would keep all the concepts from the previous version space for which we have that the label on X is correct as presented in the labeled example. Now we have two examples. We have the contrastive one as well. So we might add that and say, okay, but also we want the label for X prime to be the same as what the oracle showed us, right? But in addition, and that's that extra notch that I said, that extra crank that we use. In addition, what if the learner knows that these examples are contrastive and it knows that rule CS for the permissible examples? Then we could say, oh, and we only keep that C in there if X prime would be a permissible contrastive example for X under, oh, and this C star should actually be a C. So if C has the property that X prime would be a permissible contrastive example for X under if C were the true target concept, then we can keep it in the version space. If not, we throw it out. That's the big change that we make. And I'm going to illustrate that with a very simple example so you know what I mean by that. Before doing that, though, I'd like to say, I said initially that that first example X is somehow miraculously falls from the sky. This is just, there are different models of learning. We have passive learning where examples are just presented to the learning algorithm, but we also have active learning where the learning algorithm selects that X itself. It says, okay, I want to know the label for this point X, and then it receives the ground truth label. So those are just classical learning models. So in this talk, even though this framework here applies to passive learning, to all sorts of learning models, I'm focusing in this talk only on active learning, where the learner picks that X itself. Now, in our analysis, we focus on one core parameter. You could look at lots of things, but I like this parameter the most. This is most of my worries, is how many rounds of interaction are needed to identify the true target concept. So until the version space is boiled down to 1. And that, of course, depends on what C star is. So we're looking at the worst choice of C star, and the worst case number of interactions. And this parameter we denote by S, because usually we call it sample complexity, S of the concept class C. But I'm indexing it by CS because it really depends on that, the way I'm setting, limiting the permissible contrastive examples. So here the promised illustration of the version space update, just so that you know exactly how this works. Let's assume we have to learn a threshold in 1 dimension here in the unit interval. And I am using the following rule for my set CS. I'm saying if C star is the target concept and X is the example that the learner has requested for the label, then a contrastive example is any example that has the following property. It must have a label opposite of the label for X. And in addition, it must be at a shortest distance from X with that property. So it must be the closest example to X that has the opposite label. Okay, and now I'll show you how that affects the version space update. In the classical version space, suppose this X was chosen by the learner. The oracle will tell the learner the true label is 0, for example, in this case, and it will give this contrastive example X prime with the label 1. So in the classical version space update, this blue threshold here would be still in the version space because it labels X with 0 and X prime with 1. But in our fancier one notch up version space update, that's no longer true, because now if this were the target concept, then X prime would not be permissible as a contrastive example because it's not at minimum distance of X with opposite label. I would have had to pick this threshold here exactly as X prime. So here you can see there's actually only one concept that remains in the version space, namely this green one here, because for this concept, X prime is really minimal with opposite label to X. Okay, so in particular, it kind of makes me scratch my head because I think, okay, now this makes learning completely trivial, right? I give you this one, you ask one X and I give you the contrastive example that basically says, here is the threshold. So it might make learning trivial. And it might, and in some cases it does. And it can even be worse than this. So, and this comes basically from the fact that we put no limitations on the choice of that contrastive example set. Here's one basically trivial result. Suppose X and C are both countably infinite, but countable is important here. Then you can always define a contrast set in a way that you get a sample complexity of 1. Why is that? It's very simple. We just number X, and then we number all of our concepts. And now, if the learner samples any point X, it doesn't matter what the point X is. If the true target concept is CI, then the oracle will give XI as contrastive example. If this is the contrast set rule, that the only contrastive example for CI, no matter what X is allowed to be XI, then I can just encode the number of the target concept in the number of the example. So this contrast set rule makes, learning trivial. It's not interesting, right? So we might want to forbid something like that. We could look at properties, axioms that contrast set rules need to satisfy so that funny things like these don't happen. Instead, we can also pick natural choices of contrast set mappings and analyze those. Like, for example, the one that I showed you on the slide before. For this one, we could pick any function d that assigns a distance to 2 points in X. So it could be a metric, doesn't have to be a metric. And then what we saw previously with the threshold function is what we call the minimum distance model, where a permissible contrastive example for X is one at minimum distance from X, but opposite label. Alternatively, you could say, I want one with the same label as X, but at maximum distance. That's the maximum distance model. And these models you can vary with to make them more suitable to noise and outliers. I won't go into those technical details. And these are just two examples of what you can study. But because especially the minimum distance model seems kind of natural and has also been used in more applied machine learning research, I'm going to focus on this one for the rest of the talk. So if we analyze this model, you've seen already for the threshold functions, things became awfully simple. And yeah, this can happen. So if we pick thresholds in the unit interval or axis-aligned rectangles in the m-dimensional version of that, and we use as the metric the L1 distance, then we know if we have no contrastive examples, and we even allow an error of epsilon in the final hypothesis, in the final conjecture that the learner makes, so not even boiling down the version space to a single concept, but to a bunch of concepts that are maybe an epsilon off, then we need roughly log of 1 over epsilon many examples to succeed. Those are well-known results. But with contrastive examples, even without any error, just a single example will do for thresholds, or 2 examples for axis-aligned rectangles. So it does look somewhat trivial in that case still. But the minimum distance model does not always trivialize learning. Here's proof of that is that we have a parameter, complexity parameter from computational learning theory studies that essentially is a lower bound on our sample complexity in the minimum distance model, independent of what function d we pick. Doesn't even have to be a metric. So that holds in the finite case. Suppose X and the concept class are finite, and pick any mapping D that assigns distances in some form to elements of X. Then we can show that the sample complexity of this minimum distance model is lower bounded by a parameter that's called the self-directed learning complexity divided by 2. What's the self-directed learning complexity? SD, I'm abbreviating it. It's something that we call a mistake bound in the so-called model of self-directed learning, which is a classical model, 30 years old in computational learning theory. What does that model look like? So in this model, a learning algorithm is facing a finite set X of unlabeled examples. So that's the domain over which the concepts are defined. It will choose an element X in that set and predict a label for it. It says, oh, this X I think has label 0. The oracle will then tell the learner whether or not that prediction was correct. And the learner picks the next X and proceeds until all the elements of X have been labeled. And how is the learner evaluated? Simply the number of mistakes that it makes for the worst possible choice of C star. So C star still, the true labels have to come from the concept class, the underlying one. It's just a different model of interaction. And this has been around for 30 years, but apparently there is a connection to our minimum distance model in the contrastive setting. So why is it that self-directed complexity divided by 2 is a lower bound? I just want to illustrate that because the proof is so simple. Suppose we have a learning algorithm L that learns from contrastive examples with that minimum distance model, and it needs T rounds. Now we need to show there exists a self-directed learner, L prime, that makes at most 2 times T mistakes, right? So, and we're constructing this learner L prime by simulating L. So the learner L prime simulates L, which means L, it will first see L will query a point X and say, give me the label for X, because L is an active learner, right? So then what do? Okay, we need to give L the true label for X. So we make a prediction. We're a self-directed learner now. We make a prediction on X. We say, oh, I believe X is pink. So that maybe, in this case, is a mistake. And then we receive the true label. Somebody tells us it's blue. Okay, now I can tell L, hey, X is blue. But L also wants a contrastive example, and one at minimum distance from X that has the opposite label. So we now need a pink example at minimum distance from X. How do we get that? We're a self-directed learner. What we're doing now is we're picking the closest example in X, this one here, and we're saying we're predicting the same label as X. We're saying blue. Oh, correct. No mistake. Very good. We're saying, picking the next closest and saying blue. Correct. And again and again and again, we keep getting the closest example and predicting blue, 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 blue. So for a number of times, that'll be correct until eventually the closest example is pink and we make a mistake. We said it's blue and it's now pink. But that puts us in a nice situation because now we know this X prime must be the closest example to X that is pink. And it is hence a contrastive example in the minimum distance model for that point X. So we hand this pink example back to L, and now the first round for L is finished, 1 round. What have we made in terms of mistakes? At most 2 mistakes, 1 on X and 1 on X prime. So for each round that L makes, we make 2 mistakes. And then eventually we know L will succeed after T rounds. So we have made at most 2 T mistakes. That's the proof idea. Very, very simple. Okay, so in that minimum distance model, we have analyzed in particular Boolean functions. We picked Hamming distance as a natural distance metric in that context. And we looked at things like DNFs and decision lists. So our first result here is on the class of all 1 decision lists over M Boolean variables. And I picked this result because it shows that our lower bound in terms of self-directed learning complexity is sometimes very far off. It's a very, very, very much too low bound in this case, because we can show that our sample complexity here is 2 to the m minus 2 minus 1 at least, which means you need to sample almost everything. So, sorry, you need to sample everything pretty much. While the self-directed learning complexity, and that's a new result, we proved that too, that you can learn these 1 decision lists in the self-directed model with only a linear number of mistakes. So a 1 decision list, just in case you don't know, it's the concepts here are basically defined the following way. You have a list of tests, and each test just checks for the truth assignment to a single variable. So we could ask, is V5 equal to 0? If yes, then my concept evaluates to 1. If no, I go to the second question in the list. Is B1 equal to 1? If yes, output 0. If no, go to the next one. So that's a one decision list. It's called one decision list because I'm only testing one variable in each list entry. You can have more complex decision lists where you test more complex Boolean formulas. I'm sure many of you are familiar with these concepts. So here we see there is a big gap between that lower bound and our sample complexity. And similarly, we get a big gap for monotone DNFs with S terms, each composed of at most Z literals and using M variables. So we have a whole bunch of parameters here. So basically formulas that look like this. If S is 4, it means I here have 4 terms at most. Each term has length at most 3 if Z is 3, and I have 8 variables in this example. So here we have a form and lower bound on the number of rounds that we would need with Hamming distance in that minimum distance model. And it's again exponential, but the self-directed learning complexity in this case is only S. That was a known result. It's proven to be S. But the interesting thing is, if we change our model ever so slightly, you know, our model, this minimum distance model, using the Hamming distance in each round, if we don't use the Hamming distance, but allow the learner and the oracle to switch to a new distance function in each round of interaction. So the oracle announced, let's use this one now. And let's use this distance now. And then you can make do with S rounds of interaction, interestingly. So that's an added little twist. Now, to conclude, what we've done here is, I think we've defined the first formal model that models how we can learn from contrastive example in these various settings like active learning, passive learning, and so on. We found lower bounds in terms of other learning theoretic parameters like the self-directed learning complexity, which nicely places our model in the context of existing work in computational learning theory. It gave us some non-trivial, nice sample complexity results for classes of Boolean functions. It nicely extends to, you know, we know how to model approximate learning rather than exact learning in this setting, or passive rather than active learning, or noise and outliers. All of this can be incorporated into our framework and would be easy to study. So we still have, you know, hopefully a few more new research questions and results in us. But most importantly for you guys, I think it might have some interesting connections to Oracle guided synthesis. And I was so much looking forward to discussing that. And now I fear I don't really have that opportunity right now. But if something comes up, please do feel free to contact me. If you think this work is of any interest to you, here's my email address. I'd really like to thank you for your attention, and I hope you have some questions for me. I would also like to mention that this work was funded by the Natural Sciences and Engineering Research Council of Canada, NSERC, and by CFAR through the Pan-Canadian AI Strategy, and through the Alberta Machine Intelligence Institute. So thank you for your attention, and I hope you have some questions for me.
Let's thank the speaker.
Thank you for the nice presentation. Is it obvious that acoustic guitar is a contrastive sample to bass guitar?
Yeah, this was more of an intuition in that set of examples that I had, right? The organ and the synthesizer and the drum set.
It's a better example, but I'm not convinced that there is a canonical acoustic guitar. Acoustic guitar can come up in all kind of shapes. So I'm not convinced it's a contrastive sample.
That's true, but in the set, you know, the set X that you have in this case would probably a set of 1 million photos or something like that. And in this set of photos, it might be the closest It could be that you have this one photo of a bass guitar and you're looking. So by contrastive, I mean, in your pool of examples that you have available, the closest one that has the opposite label. In this mini pool that I had only 5 examples or something like that. For that bass guitar, this guitar was the closest one that had the opposite label, right? It seemed closer than the drum set. That's why I picked it. It was meant to just give an intuitive illustration. But of course, what constitutes a contrastive example is that's in the hand of the person who models this and defines the set CS, right? So how would you define that set CS? That could really depend on your application. And I'm thinking, for example, in program synthesis, you would define this rule CS in a way that it's something that you can easily generate in Oracle guided synthesis. If you know you have a mechanism for computing this set, this CS must be easily computable, right? So that you can provide this contrastive example. And it must be something that the learning algorithm can reason with. But yeah, you're right. I mean, you could challenge that. Was this really a contrastive example? But in my intuition, among this set of examples, it was definitely the one that was closest of opposite label. But yeah, it can.
But that suggests that perhaps the concept contrastive is a bit too sharp. And instead what underlies it is there are better and worse examples, right? Clearly, we all agree that the acoustic guitar is better than a piano.
Mm-hmm.
It's not clear that it's contrastive in your sense, but it's better. So maybe there is a more refined theory that somehow takes into account it is less sharp than contrastive, but it takes into account the quality of examples.
Yeah, and then what is as soon as let me just go back to my model. As soon as we say I call this the set of contrastive example, the set CS, right? But it depends on X and on the underlying concept. So if you're saying better example, I could call this the set of, these are the set of examples that are good for X and C star. As long as they depend on C star and X, then I could call it contrastive. But yes, I did not put any limitations on what I mean by CS, what technically I could put in there. The minimum distance model is one example, but you could have anything for CS. And in that sense, maybe the term contrastive example is maybe not good, because you could just say useful examples or good examples or special examples. They don't even have to be good. Some people might say, oh, this is a bad example, but somehow it helps the learner if just by knowing that is in that set. So you could call them special examples. That's fine. In the word contrastive example is a word that's used in the machine learning literature, where they use this very similar to this minimum distance rule in practical applications. So it has been used in training neural networks. You show, for example, to explain the predictions of a neural network, you might show a labeled example of a bird and say, this is a bird of the following species. And this bird here looks very similar, but it has this one distinguishing feature and it's a different species. So this is what usually means by contrastive example. What's usually meant by this. That's why we chose that term. But technically, you're right. It's maybe a badly chosen term, but it's a term that is commonly used, and we adopted it for our formal model.
Thank you.
One more quick question, and then we will have to move on.
Okay. Hi, Sandra. This is Sanjit. Thanks for that talk.
Yeah, I'm so sorry, Sanjit. I really wanted to see you.
Yeah, we'll catch up later. So my question is about comparing this model, learning from contrastive examples, with, I think, what is called learning from discriminating examples in the machine teaching literature that I've seen. which is also related to something in program synthesis, which is learning from distinguishing inputs. So the idea there is that the learner has a version space, right? And a candidate concept or program at a point in time. And it's consistent with a set of examples that the learner has accumulated from the Oracle so far. And now the learner asks the Oracle essentially to give a new example that splits the version space. And so it at least rules out one concept that is consistent with everything that it's seen so far, but not with this new example, right? Its current candidate is different from a concept that the new example will distinguish.
Right.
Does that make sense? So I've seen that model as well in the active learning literature and machine teaching. And so I'm wondering, what's the relation between these two? Like, is a constructive example always a discriminating example? And is it, or, are these two models, have they been compared?
Sorry. I believe that the model that you talk about is actually a special case of this. I think we could cast this in a specific, if we define the set CS in a specific way, we could cast exactly that model that you are talking about. But I think that this framework here is just more general.
That's also the what I think might be true, and it'll be nice to do that because that's a direct connection with program synthesis.
That's true. Yeah, very, very good pointer. You're right.
You.
I should have thought of that. Very good. Thanks.
Okay, let's thank Sandra again and continue with the program. So thank you very much, Sandra, for joining us.
Thank you. And sorry again that I can't be there.